And we're back. I am Cody Rivera. I am a senior student majoring in computer science and mathematics. I am working with Dr. Dingwen Tao at Washington State University, and my project is optimizing Huffman decoding for error-bounded lossy compression on GPUs. Many scientific applications are generating increasingly large amounts of data. One of these applications is hardware/hybrid accelerated cosmology code, which is a physics simulation package that simulates trillions of particles and can generate up to 22 petabytes of data in a single run. It is clear the need to be able to store and manage such huge amounts of data. One technique that can make this data more manageable is compression, which is the encoding of a large data set onto a smaller data set. There are two basic types of compression. The first big type of compression is lossless compression, where the smaller data set can be perfectly reconstructed into the larger data sets, and lossy compression, where some of the data can be lost in exchange for a higher compression ratio, where the smaller data set is even smaller. Lossy compression is the tactic that we use for this large-scale scientific data, and one of the compressors that is designed to address this is the SZ compressor, which is a lossy compression algorithm for multidimensional scientific data that allows users to specify exactly what error bound they want, which is convenient for many scientific applications. SZ is a mature project with several versions having been developed. One of these versions is traditional and for central processing units. There are also application-specific versions, such as for seismic imaging, and there is a version for graphics processing units called QSZ. Graphics processing units were originally designed to render 3D graphics very fast. However, due to their massive arithmetic throughput in up to 19.5 trillion floating point operations per second, they have been adapted for use in general purpose computing. The main power of the GPU is that you can compute in massive parallelism, launching thousands of threads to work on a large data set. Now I would like to bring your attention back to QSZ. QSZ compressor has three major phases. The first phase is the prediction phase, which applies a mathematical model to the data. The second phase is the quantization phase, which determines the error between the prediction model and the actual data. And then finally, the Huffman coding phase, which compresses the quantization codes to further increase the compression ratio. Huffman coding is what my research is focused on, and it is a classic lossless compression technique that was developed in 1952. What Huffman coding does is it encodes a fixed length code into a variable length binary code. You can see an example of Huffman coding on this slide, where a 8-character message of 16 bits is compressed into a 13-bit encoded message with a compression ratio of 1.23. Now, QSZ uses both Huffman encoding and decoding in its compression and decompression phases. And there's already been a lot of work done on optimizing QSZ's Huffman encoding. However, decoding is also important for when you want to analyze a data set after you have compressed it. But QSZ's Huffman decoding is comparatively inefficient. In fact, it takes up to 83% of QSZ's decompression time, making it a prime candidate for optimization. Therefore, my research goal is to optimize parallel Huffman decoding for QSZ. Luckily, there have been several algorithms developed in the literature that we could use for this application. One of these algorithms is the self-synchronization-based Huffman decoding, which was introduced by Weissenberger and Schmidt. Weissenberger and Schmidt use a property of Huffman codes called self-synchronization in order to smartly position threads in the compressed data such that there can be a lot of threads decoding small bits of the data at a time. Another such algorithm in the literature is the gap array-based Huffman decoding, which actually builds upon Weissenberger and Schmidt's algorithm, and instead of determining where each thread starts right in the decoding phase, this data is actually stored in a data structure called a gap array at encoding time. Now that we have identified these two decoders, my main job in this project was to adapt these decoders for QSZ applications. One of these tasks was, of course, to adapt the data formats, i.e., one of the tasks that I did was adapting the decoders from 8 bits to 16 bits, and more optimizations that I did included optimizing both algorithms so that they effectively took advantage of GPU architectures. For example, fitting these algorithms to more effectively fit the GPU's thread hierarchy, as well as take advantage of GPU's shared memory, which is a fast memory cache. Now that I had developed these decoders, it's now time to evaluate them. And for this, we used an experimental cluster called Bridges 2, which is part of the National Science Foundation's XSEED project. On this cluster, we used NVIDIA V100 GPUs, and we evaluated our decoder on several representative scientific data sets from 1 to 4 dimensions, and we evaluated both QSZ's original decoder as well as both optimized decoders that we found from the literature. As for the Huffman decoding itself, we have found that on the datasets that we have evaluated, that both decoders perform relatively well. For example, the average speedups for both of these decoders over QSZ's original decoder are 2.93 times and 3.84 times, respectively. Predictably, the second solution, the gap array solution, is faster than self-synchronization for decoding. However, the reason why we use both self-synchronization and gap arrays is because gap arrays require a modified encoder, and this may be incompatible with data that has already been compressed. As for QSZ itself, since a lot of QSZ's time was occupied with Huffman decoding itself, it's not surprising that there is a similar speedup in the overall decompressor, with average speedups of 2.19 times and 2.57 times, respectively, bringing QSZ's decoder to the power of its encoder. The next steps for our project include porting this project to different GPU architectures. The target architecture that we are planning to port the code to next is the NVIDIA A100 GPU, which is NVIDIA's current flagship GPU for high-performance computing. We additionally plan to incorporate these optimized decoders into QSZ's public repository, which we have on GitHub. Furthermore, we intend to extend the application domain of QSZ from merely scientific data reduction to other application domains, including large-scale databases. Do you have any questions?
Can you step through how the Huffman decoding works? I think you had a little bit on like slide 7.
Slide 7. So slide 7, so you have this encoded text, and in order to get the plain text from this binary Huffman encoded text, you have to walk through a tree. So the first character that you would decode from this encoded Huffman codes is A, because you first encounter a 1 and then you traverse the tree to A. And then the next character that would be decoded is, so it's 0, 1, 0. So you would go left, right, left. So the second character would be a B, and you would continue this process until you reach the end of the bit stream. So in the original QSZ, you mentioned that the decoder
has some inefficiencies, and the self-synchronization and the gap array approaches are things you worked on, and you had results for that. I just don't understand, though, can you elaborate a little bit more on the details of why? Why is that original decoder deficient in comparison to the two algorithms you were working with?
So the original algorithm that we used for QSZ's Huffman decoding was a very coarse-grained, it had coarse-grained parallelism where fewer threads decoded very large chunks of data. And this type of parallelism is relatively inefficient on GPU architectures, which favor a finer-grained parallelism where more threads work on fewer points of data.
What kind of challenges have you faced while developing your Huffman decoders?
One of the challenges that I faced was I mentioned that I had to use a type of scratchpad memory on the GPU called shared memory. And on GPU architectures, you have to be very careful in determining the size of this buffer. So what I had originally planned was to allocate a single buffer with a single size for each data set. And this would be determined by sampling the data set to determine the appropriate size. It turned out while we were about to enter the experimental phase that this method of optimizing the size of the buffer was not, it did not perform very well. So as an alternative, we actually developed a solution that allocated a different size buffer for different portions of the data, which is actually a much better solution because certain parts of the data will perform differently when different parts of the data are easier or harder to decompress.
Okay. Great job, Cody. Thank you.